Welcome to Really Weird Science, an introduction to quantum computing. That's a completely illegal slide. You did not see it. I'm supposed to do something way more boring, but they kind of knew what they were getting into when they let me do this. I am Kevin Roche. I am the chair of WorldCon 76. But my day job is with IBM Research, and I have worked for IBM Research for over 35 years. I have a bachelor's in physics from Berkeley. It took me 5 years because I kept taking extra classes. And from 1983, I had an internship the summer before I graduated, and it turned into the career that I still enjoy. And one of the things I like best is I get to do this, and not a lot of people do. I am actually also officially now, as of May, an IBM Q ambassador, which means I actually am authorized to speak to the general public or other businesses or whatever about IBM Q division and our quantum computing. Nothing I will tell you is secret. Anything that would require an NDA, I have to pass up the chain. So if you ask questions, I may have to say, I can't answer that. I am still learning about quantum computing myself. I mentioned Hamiltonians put me to sleep. Yeah, they terrorized me at college, and it never got any better. So, but that's not what we want to talk about. Anyway, if you haven't heard of IBM Research, anybody here who has not heard of IBM Research? I have to do this slide anyway. We have multiple labs around the world. I work here in San Jose at the Layman lab, built in 1986. It used to be down on the old plant site, which no longer exists. There's a Lowe's, where the research building used to be. The IBM Q hardware, almost all of it, is still currently located at Yorktown Heights at the T.J. Watson Research Center. I finally got to meet those guys. Their building looks cooler on the outside, but all that glass is the hallway. None of the offices have windows. All of our offices have windows. Up in the hills, we see oaks and coyotes and rabbits. Lots of rabbits. And there are signs everywhere warning about cattle and rattlesnakes. So, why do we care about quantum computing? There are classes of problems we cannot solve with what we call a classical computer. Classical computers count, they count very well, but they run into trouble with certain kind of problems. One of the simplest examples of this is the seating chart for your wedding. If you have to put 10 people at a table, there are in fact over 3 million combinations. And that's before you start taking into account who broke up with who, who's sleeping with someone else but they don't actually know about it anywhere else, and who's allergic to somebody's perfume. And that's just the first 10 guests. So, another example is with proteins and complex molecules. There are 3 or 4 dimensional problems actually to solve. And you can approximate things, but to actually get exact solutions would take too long. There are too many combinations to go through. What all of these problems have in common is exponential scaling. And there is a classic story of the sultan who promised to pay a worker in grains of rice on a chessboard. 1 grain on the first, 2 on the second, 4 on the third. That sounds cheap. Well, the sultan did not understand exponential scaling because in fact, the story, there are different versions of the story. In one of them, the peasant is executed before they bury the country in rice. In another, the vizier who agreed to it is executed. And in another one, the people overthrow the sultan and eat all the rice. But this exponential scaling is a class of problems you can't solve just by counting or by doing ands and ors. It just doesn't work. They get out of control too quickly, and you cannot reduce what we call the solution space to something you can solve by counting. So instead, we want to take advantage of the weird world that is quantum mechanics. So we're going to take a short dive into some of the critical topics in quantum mechanics that make our quantum computers work and are the general idea behind most of them, however they build their hardware. So we're going to start out at the edge of the galaxy, I hope. Come on, there we go. Okay, the edge of the universe, thanks to Google Universe. You may recognize the neighborhood we live in. And this is what you do when you're homesick with bronchitis and have to Replicate Pro. We get to our local neighborhood. There's our friend Saul and our nearby neighbors. And we're going to go visit Yorktown by way of the moon because, well, I had to duplicate that. So Earthrise. I mentioned Yorktown, upstate New York. This is actually the IBM Q lab. And you may have seen pictures like this. We're diving down into our circuitry, but we're actually going to go past the circuits. We're going to go down into the crystalline structure, all the way into our friend, the atom. We've all seen pictures like this. We all grew up. We know the atom. We know that lovely little miniature solar system. This is the Bohr model of the atom. The nucleus at the center and all those electrons whizzing around it, except that isn't really what we'd see if we had our hypothetical quantum Voyager. We would not see orbits. We would instead see this big fuzzy mass in front of us, reflecting what we call orbitals. Come on, you can do it. There we go. These are, in fact, the orbitals of the sulfur or argon atom. You can't even see the nucleus. It's too small. And what these are maps. These big fuzzy balloons are maps of where the electrons might be. Because the problem is that when you get down to this level, the common sense stuff we know about things moving around isn't common sense anymore. The first really weird fact of quantum mechanics is that things are fuzzy at the quantum level. How many of you have heard of the Heisenberg uncertainty principle? Oh, good. So what that is, really, is that there are properties of a system that are linked to each other. And there's actually a fundamental limit on how closely you can measure one with respect to the other. One of the classics is position and momentum. And momentum meaning the vector velocity. So that's not only how fast is it moving, but what direction. So if you know exactly where something is, you no longer have any idea where it's going. Conversely, if you know exactly how fast and what direction it's moving, you don't actually know where it is. Doesn't make sense to our macroscopic world brain, but it is fundamental. And related to this, because of this fuzziness, is something we call superposition. So I can take a snapshot of my atom, for instance, and find out where the electron is at a moment. And I can do it over and over and over. And I will build a map of where the electron might be, but I never know how it's getting from point A to point B, and I can't predict until I measure it where it will be in that map. The equations tell me what the shape of the map is. That's what gives us those nice big fuzzy balloons. But at any particular moment, until we take a measurement and do what we call collapse the system, we don't know where it is. This is weird. This does not match what we think about normally. How many of you recognize this? It's a magic 8 ball. How many of you have never seen one before? Wow, okay. So in the magic 8 ball, there is a dice, a 20-sided die floating in colored water. There are 20 possible answers on it. 20 possible answers all superposed on top of each other. When I turn it right side up, I measure. I get one answer. It's upside down. Ask again later. Now, if I do this over and over again, if I do it 100, 1,000 times, I will in fact discover that 50% of the time I get a yes answer. 20% of the time I get a maybe or ask again answer, and 30% of the time I get a no answer. So that is my map. But every single time I turn it upside down, all 20 answers are superposed. Until I make a measurement, I don't know what that measurement will be. I just know the possibilities. And this is one of the most powerful parts of quantum mechanics that lets us model complex systems, because the possibilities are superposed until we make a measurement. The next thing that we care about is quantized energy, which is where quantum mechanics has wanted its name. Remember that map I showed you, all those big fuzzy balloons? So when we build a system, it turns out that at the quantum level, you can't have any particular energy. They're predefined by the state of this, by the nature of the system itself. So you've heard of quantum jumps, which again, quantum leaps. Well, I like a television show, but quantum jumps, that's the space between the allowed levels. And there are rules for where things can jump between the energies. But if I, for instance, give something half the energy needs to go from 1 to 2, it won't actually move. So when we build our atom, we start filling at the bottom, and it turns out electrons have 2 flavors, up and down. And so we fill it up with all the flavors, and you can see our map there of fuzzy balloons is starting to fill in. And so here we are, we have all of them. That's our argon atom. Now if I take one out, I now have a space where I can move things in and out, but they can only jump by that particular energy amount. And we need this to build our quantum computer because we can artificially create those levels. And we'll talk about exactly how that works a little bit later. Then the other thing. How many of you heard about entanglement? How many of you have heard of quantum teleportation? How many of you think that means faster than light communications? Very good. All right, so entanglement, it turns out if you have 2 systems, here I've got fuzzy pink clouds representing electrons. Remember I said they have 2 flavors, up and down? So if I have 2 of them and they're entangled, I know that my total up and down is 1 up and 1 down. Once they're entangled, if I measure the first one, I know what the second one must be. But these correlated states exist across space. So once they're entangled, I can move them apart. The famous teleportation experiment done with the International Space Station by the Chinese scientists used photons, used laser light. They separated them up from the ground to orbit, and they stayed entangled. Now the trick is, so when I measure my first one, boom, now I know what the other one's going to be. I can't use this for faster than my teleportation because my friends on the ISS need to know when to measure. If they measure too soon, they're going to lock my end. And so what that means is, the reason you can't get FTL communications is the information that it is time to measure travels at the speed of light. I've got to pick up the cell phone and call ISS and say, okay, measure now. And no matter how fast I do that, it's not going to be faster than the speed of light. But we don't care about that part for building a computer. We just want to be able to tangle up our quantum states and use that to make computations. That lets us open up that solution space I was talking about. Oh, there it is. The cheesy animation. I know I forgot something. So, what does all this weirdness do? Well, first of all, what does it do in the real world? Chemistry. So, one atom is a quantum system. When you have more than one atom in a molecule, those fuzzy balloons blend into each other. And that is called hybrid orbitals. So my favorite hybrid orbitals are in benzene, the infamous ring molecule. So those balloons sticking up and down are called the P sub Z orbitals, but it turns out they blend completely into these amazing toroidal balloons of possibility and probability. And so that means the electrons in those orbitals, these pi orbitals, don't care which carbon nucleus they're associated with at all. They wander around in that whole ring anywhere they want to be, and you know what that gives us? That gives us life. The fact that those electrons are so delocalized and can combine in so many different ways and so actively is where organic chemistry comes from. And that's why we live and breathe, because of organic chemistry. The other thing we get from quantum mechanics that you see every day, we're standing underneath it, is light. So, remember, energy to move things up and down. If they drop down, that energy has to come out. It comes out as electromagnetic energy. And if the gap is the right size, it's a wavelength we can see by. This is a fluorescent bulb. It's happening twice in a fluorescent bulb. Inside there is argon gas. We shoot a spark through it. That excites some of those electrons. They drop back down. They give off ultraviolet light. Can't see very well by that, but we coat the inside of the tube with a pigment. The pigment is excited by the ultraviolet light, and when they drop down, the electrons emit visible light. So, bingo. We've got quantum mechanics happening twice, just so we don't trip when we go into the bathroom in the middle of the night. But even simpler, the LED does this at 5 volts. We don't need any of this fancy spark stuff. We apply 3 or 5 volts across a diode with the right pigment, and it will light up for us. Now there's a little secret about the new LEDs. The white ones actually work the same way as the fluorescent bulb. The diode makes UV light, and a white pigment glows inside the LED. So quantum mechanics is around here all the time, and makes everything we do possible. We want to do something new with it. We want to go from quantum mechanics to quantum computing. So, in 2000, David DiVincenzo came up with a model for which he needed to build a quantum computer. Quantum computing scientists love their long words. Let's try and break this down. So, what we want to do is to be able to make what we call a qubit, a quantum bit. So, we need a way to make qubits. We need a way to set their starting conditions to do input. Quantum mechanics are slippery, so if we can't hang on to our qubits, we can't do anything with them. We need them to last long enough to actually run a calculation. We need to be actually able to do operations so that they're doing something useful for us. You know, it's really cool we can set up all these qubits and then we just stare at them, but it'd be better if they did something useful. And then when we're done, we have to be able to read out each qubit and know that we're reading the right qubits. So this qubit-specific measurement means when we go and measure the system at the end, we know which qubit we're looking at. There are lots of ways to do this. What we want to do is build a very simple model of an atom. You saw that argon atom had all those different levels, and there's all of these different ways things can bounce between them. We want something much simpler. We want 2 levels. We want 2 levels that we can tell apart because the radiation that comes off it will have a frequency dependent on the gap. So you can see that, let's see if this works. It works, all right. So this one is a different height than this one, and this gap is different than this gap. More importantly, we have a third one, which is even different yet. So if we get into that state, we know something's wrong, and we can ignore it. So, 3 gaps, all different, so we can tell them apart when we get to the measurement state. It also lets us set them up. So, atoms are very small, they're hard to build. Let's not build an atom, let's build something else. So, one way is you can take our big atom and pull 1 electron out. It's now an ion, it's easy to hang on to because it has a charge, and there's only 1 empty energy state. However, they all tend to have exactly the same empty energy state. That can be tricky when you're trying to find them later on. Superconducting qubits, which I'll talk about a lot, are another way to do it. So I will come back to this, because this is what we're doing. You can also, in theory, do it inside a solid matter by picking one system and perturbing it. So it's what's called the color center, and so it's different from the others and you can excite it. Lots of research gets done this way. It's hard to build a machine out of it. You can, in theory, do the same thing with nuclei that we do with whole atoms, but that again requires a whole lot more equipment. You can do it with light, but then you're mixing electronics to control everything with lasers inside the system. I've done that with macroscopic experiments. I can't imagine doing it at the quantum level. And there are things called quantum dots, which I don't understand. And in theory, we could do it with our neutral atom, but again, then they're slippery because they're self-contained, and doing what you want to them and have them behave can be tricky. So I mentioned trapped ions. They're nice because they have the charge, And there's a lot of good work being done with trapped ions. I don't want to minimize that. However, their frequencies are usually optical, meaning you have to use light and lasers to talk to them. I'm going to come back to what we do now, which is the superconducting qubit, more specifically the transmon qubit. How many of you have built electronics for fun at all? How many of you have built oscillators? A few? So what we build here, let's go away, we use something called a Josephson junction, which is a superconducting element, to build an anharmonic oscillator. If you build an LC circuit, so that is an inductor and a capacitor, the capacitor holds a little charge, the inductor slows it down, and you start it ringing, it will just ring back and forth at a fixed frequency, or its harmonics, its multiples, happily, until chaos wears down the charge. But you can get it going and it will ring. The Josephson junction is what we put in place of the coil because it doesn't have harmonics. The frequencies for it are not multiples of each other if you look at the energy. And so the drawing, oh look, it's exactly the same idea. We have three very different energy levels, which means three very different frequencies that aren't multiples of each other. So now we can talk to it, and we know we're talking to it the way we want. As it happens, the devices we build work at microwave frequencies. But we can make them with regular circuitry techniques, which means we can adjust the size slightly, and every single qubit has its own frequency. So we can talk to one and only one qubit. The actual qubit is this square, and inside the square is this shape. And these big things, they're slabs of niobium separated by space, so they form our capacitor. They will hold the charge as the system is ringing. And in the very center is this little thin crossing, and that is two little layers of aluminum with aluminum oxide between them. That's our Josephson junction. When you cool it down, the aluminum becomes superconducting, and you get this weird stepped energy that is only allowed across the junction. But as you can see, the whole thing is actually fairly large in terms of electronics. We're nowhere near the limits of what they use for building transistors. And so we can crank them out over and over, and we can tune them, so each one has its own frequency, and we can make them talk to each other. And that's what this is. These squiggly lines are microwave antennas. So we have a set that come in from the outside that let us talk to a qubit, and then we have sets between the qubits that let them talk to each other. And this is the trick to making our system of qubits. The one other thing that's really important, so these little red things here, those are the ends of the squiggly lines. You notice they don't actually touch. There's no direct electrical connection between the outside world and the qubits. Once we get them going, they're in their own little universe. And that actually is part of the quantum weirdness. So we do cool this down, way down, to 15 millikelvin. That is colder than space. And I'll show you the refrigerator a little later. They're pretty cool. So that was a 5-qubit board. This is a 16-qubit board. You can see it's the same idea. All the squares with qubits, all the squiggly lines, so they can talk to each other. And this is how we scale them up. But it's still standard circuit board and microcircuit technology. The materials are slightly exotic. Niobium is no fun if you're trying to make boards, but we're not doing anything so small that it's miraculous. And in fact, we don't want them small because the size is how we tune the frequency. We need them to be big enough that we can adjust that capacitor. So once you've got them, we've got these qubits, what do we do with them? So my colleagues frequently talk about the fact that quantum bits, qubits, and yes, it is a joke, physicists and their puns, can be both a 1 and a 0. But what they really are is any possible superposition of 1 and 0. And that means some number times the 1 state added to some number times the 0 state. And those numbers can be anything. Real, simple, integers, well not integers because we get a value of more than 1 total. But they can also be imaginary and complex. So what we do is we map them on a sphere. Each qubit is actually in its own little universe of probability space. We call it Hilbert space. So a qubit, when we look at it, when you measure it, we can only look in one direction. So we look through that little window. There we go. There's my qubit. So my qubit is this arrow. It's exactly one long, touches the edge of the sphere all the time. So if it's pointing towards me when I measure it, it's a 0. If it's pointing away from me, it's a 1. But we can point anywhere on the sphere. Now I can only measure towards or away. So what I have to do is measure it more than once, which means set up the experiment and do it again and again and again. And here we go. So we're measuring up and down over and over and over and over, and we get the ratio of the ground state, the ket 0, to the excited state, the ket 1. And the ket is this weird notation. There's the other side of it, which is the less than sign with the vertical bar. That is the bra notation, and together they form brackets. Again, physicists and their puns. But this idea, now, you notice I can only tell the ratio. I can't tell which way around the circle it's pointing. And this is where we can get all the power of the quantum computer. You can build a classical computer that lets you have mixed 1 and 0, but it would be a disk, not a sphere. You can't do the phase space. So what we can do is rotate. So an Xscape flips it 180 degrees around the circle. But we can do other operations that essentially move our peephole. So if I move what we call a Hadamard gate, I've effectively rotated my window away from the 0 axis. And this now lets me look at a different axis. So if I have that one state and I've rotated it through a Hadamard gate and I measure it, I now have a 50% chance because it's completely superposed now between ground and excited. If you actually measure it on a physical qubit, you typically get 45 to 55 because there is quantum noise in the system and it's an actual physical object we're measuring. Then there are way more complicated ways you can rotate everything so you can explore the rest of that sphere when you get to the measurement point. And then that's just one qubit. The moment we add another qubit, we can tangle them up and we become a system. And we can keep doing that. So now I have 4 basic states and a linear combination including complex numbers of all 4 of those basic states. And that's just with 2 qubits. Every time we add a qubit, we add another dimension to the solution space. And with the entanglement, once you've entangled them, that persists. So if we entangle one with the next, and that with another one, down the road, if we do something to the first one, it instantaneously affects all the qubits that are entangled with it. Lots of notation. We won't go through the math, I promise, because it still makes me dizzy. When we run an experiment, we go right back to that checklist. We reset the system. We then set up everything in what we call the ground state. Then we encode it. And this is the part I'm no good at yet. But that means some of them will be flipped to 1s right away, so we may have a mix of 0 and 1s once we start the problem running. And then we have a sequence of those operations, what we call gates. And then we say go. And we do all of this with microwaves. When we're done, we measure it. And then we do it again, and again, and again, and again, because each time we only measure one of those possible solutions inside that multidimensional state. It's crazy. This is where we get back to the magic 8 ball. When you have more than 1 qubit, you get more than 2 answers, right? So I don't have an n-dimensional magic 8 ball. IBM Q itself looks like this. Well, this is just the wires. Remember I mentioned it has to be cold. The chip itself is about a centimeter on the side, and it lives at the bottom of a very dark and very cold refrigerator. And in 2016, we made it available to the public, which was a big deal. That was when I first got to start talking about this, and that's what ultimately led to what I'm doing now. It looks like this. It lives at our lab. We have several of them now. The chips I showed you, and then there's a web interface for you to play with it. And I mean all of you for free. I'll show you how to get there. We think of it now as we're at this point. We're still nascent technology. We've actually solved problems with our brand new tiny quantum processors, but we're still just at the very beginning of what we can do with these. Scaling is a problem. We can fit 20 qubits on a chip. We have one chip with 50. Last May, actually 2 days ago, this is a big deal because that's Times Square, and the Yorktown lab and one of the researchers is on the big TV in Times Square when we revealed the 50 qubit processor. Yep, it's a big refrigerator. But it was a big deal for us. It's beautiful inside, you can see. And there's a reason for that. Every one of those disks that goes across the center is a temperature change. And because if we ran a solid wire from the top all the way to the bottom would stay at room temperature. So every one of those disks is a temperature break. The microwaves can go across it, but it's not a solid wire. The chip lives in this can at the bottom, and then, to give you an idea how big it is, that's me standing in front of our copy. This one's traveled around the world. Unfortunately, it's not in California right now, or I would have had it here. I tried really hard. And it's just this beautiful thing. And the way it works, you remember I mentioned we're at microwave frequencies? So, have you ever, anybody tuned a guitar by resonance? Where you get the first string tuned, and then you fret it to match what the next string is supposed to be, and pluck it. And when you've got the tension adjusted right, the second string, the unfretted string, will ring in response. We do the same thing. We sing to the qubits to get them going, to inject enough energy so they start oscillating, and then we listen and they hum back to us. To do all those gates, we send little tiny microwave pulses, not enough to bump them out of what they're doing, but enough to nudge them, to rotate them in that sphere of probability and make things happen. And to make them talk to each other, if you sing to one qubit at the next qubit's frequency, it entangles them. It's just, excuse me? So the way we entangle these qubits, the squiggly lines between the qubits, if we have qubit A here and qubit B here, if we sing to qubit A at qubit B's frequency, some of the energy goes along that squiggly line and entangles them together. And that's how we can control the entanglement. And across the chip, we can do that repeatedly, so we can end up with a chain from corner to corner of entangled qubits. Then the trick is using that before chaos sets in, because chaos is part of quantum mechanics. So I mentioned the chip. It's in that little thing there. The new chip, the 50 qubit chip, is actually more than one layer. The 20 and smaller are single layer chips. And I do not actually have, I am not privy to the actual schematics for the 50. But like I said, the cool thing about this is you can actually play with one of these for free. The public, anybody. We have clients who pay for access to our 20 qubit processors and are working with us on developing good uses for quantum computing, but the public can use 5 and 16s for free. You search for the IBM Q experience, that's the fastest way to find it. And you'll get something like this. This is what it looked like the last time I visited. The web designers like to play. And it tells you all about Hello Quantum, which is a quantum computing game for your phone or your iPad. It took me 2 days to do levels 1, 2, and 3, and then a month to figure out level 4, which is when we started getting entanglement. But you can also start writing code right away. You create an account, and it's like a freemium game. You get so many points. You can run as many simulations as you want. When you want to run something on the real processor, you say, go, and it goes into the queue. Your points go down, and then they come back up once your job is done. And this is so somebody doesn't, run a random number generator that I wrote, every 10 seconds on the main processor. That would be frowned upon. But I can run it on a simulator as often as I want. So when you get there, the introduction. Don't go here. Believe me, don't go there unless you are already a probability mathematician. Go here to the beginner's guide. And I haven't even opened this. That's actually not quite true, but the beginner's guide actually covers some of the slides I showed you are out of the beginner's guide. It was written by Talia Gershon, who started our quantum outreach program in 2017, and I've also stolen a bunch of her slides. The wedding reception slide is hers. It gives you an introduction to what we're doing, and there are tutorials, examples you can try right there in the simulator as you're reading it. It's really weird. The reason we have this public thing is quantum computing requires a kind of sideways thinking. And it's not like classical coding, it's not linear. And figuring out the best algorithms and the way to do things requires a different kind of thinking. And so we want people to play with it. So the ones who are good at it, figure it out, and then help make quantum computing better. So it's a very, very early nascent technology, and we figured the best way to make it better is to have more people working on it. So it was the first quantum computer on the cloud. The last time I think these numbers have actually gone up, but over 85,000 users in the system, all around the world, over 4 million experiments run on the real processors, papers, and not just written by IBMers. People are actually using our quantum computers to write papers. This is pretty cool. We have colleges, universities, high schools, programs around the world. And like any, let's see, this is a map from May, activity running on the processors, where the jobs are coming from. And there's also the community. Because like any public computing platform, there are people involved. So there are resources for learning how to do things better. Qiskit, I'm going to come back to in a minute. But this is what you see when you actually start programming. We call this the quantum composer. And this is how you program the 5-qubit processor. It's like writing music. You add operations, drag and drop them on the screen onto the lines, and then you say go. The lines represent time. Each line is a qubit. And the pink block there means measure. So once you've measured it, that qubit's locked. You do all the things and then you measure. When you're done, you get an answer that looks sort of like that one I showed before when we were counting over and over. It's exactly the same idea. Up here, you tell it in the settings. Where are the settings? Of course, it's not on the screen. You tell it how many shots you want to take, how many times you want to measure. Just different examples of different compositions. This one here, that's the C0 gate. That's one of the ways to entangle things. And all of these examples are in the tutorial, and you can try them, and you can confirm that you got the same thing that the tutorial said it was supposed to do. And then you can get into more complicated things. I haven't got here yet, I will be honest. They keep breaking things in my lab, and I have to put them back together. Because material science means I'm working with physical objects. And I have about 20 people who like to break my toys. Some of the staff, this is from a couple years ago, but I've met now a bunch of these crazy people. They're all kind of crazy, let me tell you. And this is more of the projects around the world. These are the universities involved in working with us. We're building what we call the IBM Q network, which is clients and schools and people who are using the system and helping make it stronger. My favorite is Dr. Merman, who while working in Antarctica, in between field work, would write quantum computing programs. There's also the craziness. So we have papers, but more important, we have quantum battleships. We have, how the heck do I make this work? A lot. What are your favorite quantum jokes? I stay out of that one. And one of the longest threads in the forums is, how can you write rock, paper, scissors with a quantum computer? It's like any programming community anywhere, we're nuts. The good kind of nuts. And then there's Qiskit, which I mentioned earlier. Unfortunately, my Raspberry Pi, which I was going to hold up here and have it run a job on the quantum computer for you, I can't get on the network because I didn't bring a keyboard for it. It's my own fault. It doesn't know this Wi-Fi yet. But Qiskit is a Python library that lets your code talk to our quantum processors. And so if you want to write something more complicated than you can do with a pretty composer, there is a symbolic language called OpenQASM, Quantum Assembler, which I've been informed by my colleagues is pronounced OpenChasm. I'm not sure why they named the language for a yawning abyss, but that's how they pronounce it. And it's really powerful. So I actually literally did write a random number generator that puts 5 qubits into superposition and then measures them, because I wanted to get a different answer each time it came back. And I had a little LED matrix to display it on, and I displayed it in the shape of the 5 qubit board. It's great at the Maker Faire because I can hold it up, it's bright. And I was going to do it for you, and it didn't work. So sorry. And Qiskit now has its own website. It's on GitHub. It's qiskit.org. Introductions, how to download the package. And again, you can play with it for free. And then we get to what we're calling the IBM Q network, which is, we are of course hoping to commercialize this. We're beginning to commercialize it, but it's still nascent technology. So we have what we call hubs, which are regional centers of expertise. Obviously the first one is in Yorktown, but we already have universities on several continents that are acting as hubs. We have partners who are looking at what could it do for my specific industry. So they're actually working with our experts and their experts to see what can happen. And then there are lots of startups who think quantum computing is probably the next sliced bread, and they don't want to miss out on it. Some of these will work, some of them won't. One of the things I don't talk about, so don't ask any of these questions, we don't talk about case studies or possibilities yet. The technology is too new. But it has actually been used for some real things. Let's see. This is my favorite. Last year, or the end of 2017, rather, a paper in Nature using one of our quantum processors modeled completely, calculated all of the states of the beryllium hydride molecule. It's only 3 atoms. 1 beryllium, 2 hydrogen, and it couldn't be calculated, not approximated, could not be calculated classically. That's why it was on the cover of Nature. And the fact that we could actually do that, use quantum mechanics to calculate the solutions to a quantum system, is the first sign that yes, this is actually a useful thing. It's not just a novelty. We talk about quantum volume. Lots of our esteemed competitors talk about how many qubits we've built. What's important is what can you do with them. If they don't talk to each other, you can have 500 qubits on a chip, but if it's noisy and they can't talk to each other, you can't actually do anything with them. Qubits all by themselves are nice little quantum systems. When you can get them to talk to each other and you get the error level down so they last long enough to do useful algorithms, then you build up what we call the quantum volume. So right now, the technology is in here. So all we have to do is actually reduce the error level, and we get a lot more power right away. And this is not speed. Quantum computers are not faster than classical computers. They explore the solution space using quantum mechanics in a way that we can't get at with classical computers. So it's not a question of gigaflops or throughput, it's a question of can we model something quantum that we can't get at classically? And they're always pushing how well they can model things classically, so it's a race. But we do believe there are problems that cannot be solved except with quantum mechanics. Now what we want to do obviously is really go this way and get to those nice big blocks. I'm ahead of myself. No. So this is what I'm talking about. Lots of qubits with bad error rates doesn't do any good. A few qubits with lower error rates can make a big difference. what we really want to do is both. So we are out and about. We had a booth at Maker Faire this year in San Mateo. We got the editor's prize, the editor's choice award for our commercial IBM quantum computing booth. That was a very pleasant surprise because it was Maker Faire. I talked to, I think, 20,000 people that weekend. This little thing here, this is the predecessor to my Raspberry Pi board. My friend Noor built that, and I was inspired to build one that I could hold in my hand. Because that one was on the bench, it was hard to see. And this will still work. This was the barcode they gave me last year. But it's easier to just look for IBM Q experience to get into the doorway. I know I've gone fast. It's a little bit of quantum mechanics that can open the door to a whole different world of possible computation. And I have time for a few questions. Yes?
Great talk, thank you. Two questions, very different, really quick. One is, and I may say, nobody knows, but you presented the problem at the very beginning of your talk about turning the writing table. So could you get some feel, using some of the terms you've used, about how you might start to solve that problem? Second question is, you know something about quantum mechanics? There's a lot of useful quantum mechanics, very loosely, in science fiction and quantum movies, which drives me crazy because it makes assumptions that just don't make any sense.
Okay.
Does it bother you?
All right, so the first question is, where are we in actually solving the wedding table problem? So this question of algorithms is the big deal. We think there are three areas of problems we'll be good at solving. One is quantum mechanics, like beryllium hydride. The next is optimization, and that is the wedding table problem. So there are people developing libraries just for that. Algorithms dedicated to, if you do it right, if you build your model right, and you do all those measurements, the right answer is the one that sticks up out of the noise. If you do it wrong, all you get is noise, or if it's time to retune the quantum system, because every so often things get noisy and then they warm it up and they cool it back down and then it behaves itself again. It is a physical quantum mechanical system, and sometimes, you know, it's like when the cable goes out, you know, turn it off, turn it back on. It takes about 36 hours to cool down from room temperature to 15 millikelvin. So, not great, but pretty fast. The other question was, does the misuse of quantum mechanics in science fiction drive me nuts? Yes. Especially when they make assumptions about the math from knowing a little bit. Here.
What's your best guess as to how we will be building qubits in 100 years?
So the question is, what is my best guess to how we'll be building qubits in 100 years? I don't have an answer. The transmon qubits are being explored by several companies, including IBM. They are nice because, at least for now, they're easy to scale. They use manufacturing technology we know. We don't know what the limit of scaling the size of the system is. We're learning what the problems are as we build bigger ones. So I don't actually have a good answer. Right now, we're focusing on the transmons, but it may be that trapped ions or some other system will prove to be more useful for a large system. To do a full, fault-tolerant, universal quantum computer, which is the ultimate goal, you need thousands of qubits to handle the internal error correctly. So getting up to that scale is the big technological challenge. That's why we describe this as nascent technology. It's also why it's an IBM research product, not an IBM product, because it is still in development. Back there in the map.
True random number generation, is that part of the capability of quantum computing?
The question is, true random number generation part of the capability of quantum computing? Yes. Maybe. The system is not perfect. It's physical. So there is random probability from the fact it's a quantum system, but there are also can be variances in the system. What I do with my little program is I only take 100 shots. If I took 1,000 shots, I would get absolutely even values for all the possible combinations. By taking too few, I get a random number back. So I'm deliberately crippling my calculation to get a spike back. So that's how I do random number generation. So I'm not going to have a better answer than that. I'm using a trick to get it.
You talked about
You can run these programs until random numbers, random chaos destroys the system. Are we talking milliseconds, seconds, minutes? How long can they run?
I believe we're in the hundreds of nanoseconds. So people often ask, what about hybrid classical quantum systems? All the quantum computers are hybrid. You use classical computers to set everything up and say, go, because they can twiddle the microwaves way faster than a laptop can. And I actually have to be similar. So I get one more question? Right here in front of you. Ooh, rough question. Do I think creating artificial intelligence will require the use of quantum computers? My cognitive computing friends would probably say no. However, because quantum computing is I know it's a buzzword, but it is a different paradigm. It's a physically different thing we are doing. It's a way of expanding the possible solution space. So I think if we are trying to build a powerful art, this is me speaking. I'm not speaking for IBM. Personally, I envision that hybrid systems are going to be the way. Classical computers count. Quantum computers can explore these giant solution spaces. And I think ultimately AI is going to want to be able to explore those giant solution spaces, so it will take advantage of what quantum computing can do. Quantum computer is never going to balance your checkbook. That would be a waste of power. The reason it's so cold is not just to make it superconducting, it's because it's quiet at quantum level. So even if we have a room temperature superconductor, we probably want to cool it down, because otherwise all the wires are getting off stray emissions. We want it in the deepest, darkest, coldest, quietest place we can build. And that right now is what we're doing. And it's pretty cool. Please go out and play with one. I will be out on the floor for part of the afternoon, but I do have to run right now.